in the next example, we've got a mass going in a vertical circle on a rope, speed of 2.5 meters per second at the lowest point. So lowest point down here. Think about, okay, what forces are acting? Got gravitational force downward, tension upward. So when we write Newton's second law, tension is in the direction of the centripetal force toward the center of the circle. mg is in the opposite direction, so we got T minus mg equals mb squared over r. So the tension then is mb squared over r plus mg, and we could plug in numbers and get a value for that. I'm not gonna go ahead and do that. You can plug in those numbers and get a number, numerical answer if you want to. Continuing on, example 8. Oh, this is a fun one. So, banked curve. So again, our car is over here. Icy is a keyword in physics world. If we're on ice or it's icy, that means our surface is frictionless. This gets more complicated with friction. So be glad there is no friction. So what forces are acting on this car? Got gravitational force and normal force, and that's it. Now, the center of our circular path is over here somewhere. So this is actually a case, even though we're on a slope, it's better not to rotate the coordinate system because our acceleration is only in the horizontal direction. It's toward the center of this circle, and the circle is horizontal. So better not to rotate the coordinate system. So this is theta, which means by alternate interior, this is theta, which means this is 90 minus theta, which means this angle is also theta. But the angle between the normal force and the vertical is theta. So if you look, the normal force is the only one that has a component toward the center of the circle. Looking at our angle is adjacent to the vertical, opposite the horizontal. The horizontal is where our centripetal acceleration is. So when we write write Newton's second law in the horizontal direction, we have normal force sine theta is equal to mb squared over r. In the vertical direction, we have normal force cosine theta minus gravitational force is equal to, you guessed it, 0. So this looks a little bit different than any expression we've gotten before, but in this case, the normal force is equal to mg over cosine theta. And then we can plug this in. Normal force is mg over cosine theta. And you notice mass goes away. Sine over cosine is tangent. Multiply the r over. So we get gr tangent theta equals speed squared. Take a square root. That's the speed we have to go at to not use friction to go around. Next up, this is a fun one. This can be tricky, a little bit tricky to visualize, but this is something that a ride that is at carnivals. I've been on a ride like this. So let's say this is just a little pen holder that I have. This is a top view of what's going on in this carnival ride, and it starts spinning. And it spins faster and faster and faster. And as it spins faster and faster and faster, you feel like you're pressed up against the wall. So it spins faster and faster and faster. You start going around, you're going around the outside, and you get pressed up against the wall. You're the pencil. And then eventually you get going fast enough that the floor drops out and you stick to the wall. You don't actually fall down. It's kind of neat. But so this is our situation. If we take a top view, this is you. You're at the top of your head. The only force acting on you horizontally is the normal force from the wall. That is supplying the entirety of your centripetal force. If we take a side view, this is the wall. This is you up against the wall. You've got gravitational force on you going down. And then after the floor drops out, the only thing holding you up is friction between you and the wall. Static friction. Okay? So in order for your people not to fall, what do we have to have? Well, the maximum static friction, the maximum static friction, mu(s) times normal force, has to be enough to hold you up. So you have to not accelerate in the vertical direction. In the horizontal direction, you have only normal force contributing to the centripetal force. So your normal force is equal to mv squared over r. And you do a quick substitution. Plugging in for normal force here, mu(s) mv squared over r minus mg equals 0. So we can say equals mg. Sorry, mass cancels out. And what do we have? gr over mu square root. So the walls of the chamber have to be moving that fast in order to keep people up against the wall. Notice mass is gone, it canceled out, so it doesn't matter. You could have somebody who's really fat or somebody who's in really good shape and still need the same speed to get them to stay up. One last example here. Got a block of mass m sliding down a frictionless track, descending from a height of 5r, then around the inside of a circular loop of radius r. So this has a radius of r. We start from a height of 5r. And it's frictionless. So to determine its speed at the highest point, we can apply conservation of energy. Sorry, let me draw a better loop here. Okay. If the loop has radius r, then its height at the highest point is going to be 2r. So initial energy, mgh, is equal to final energy. The radius is r, we're at a height of 2r, plus kinetic energy. So 5 minus 2 gets us 3, mgr equals half, mv squared, mass goes bye-bye, multiply by 2 gets us 6. So the velocity at the highest point is root 6gr. Then we think about the highest point here. What forces are acting on this? We have gravitational force downward. We also have a normal force downward. We don't often have downward normal forces, but at the top of the loop, the track would push down perpendicularly on the rail, the block. So both of those are contributing to the centripetal force. They're both in the same direction. So writing Newton's second law, we'd have normal force plus mg equals mv squared over r, the radius that was given to us. So normal force is equal to mv squared would be 6gr minus mg. And we notice r cancels out, so we have 6mg minus mg, so the normal force in this case would be equal to 5 times the block's weight.